let's go ahead and get started. So did you guys have a nice break last week, like last Wednesday?
Yeah.
And start to forget everything that I have talked about in this class? Yeah.
How's the trip, Professor?
The trip to Career Fair, the Career GPS, that was interesting. That was an interesting one. More students this year were aware of computer science and programming than last year. It was just 1 year ago. Okay, a lot of students walked by, and I kind of asked them, "Are you interested in computer science?" And many were interested. Even though my booth was at the wrong place, I got kind of bundled with business technology, all the financial institutions. Golden one was in the same building. I wasn't with the technical stuff, on that day. And still, many students walked by, and when I asked them, are you interested in programming, computer science, and many, expressed, interests. So something changed. Okay, I think the awareness has changed. Part of that has to do with Silicon Valley, like Facebook, Google, and many of those big companies. They have been pushing very, very hard to have middle school and high school to include programming or computer science as a part of its curriculum. And the idea is to produce more people who can work in these companies as software engineers. And why do you think that is the case?
Cheaper.
Exactly. Okay, they want to hire engineers that do not cost as much as they do now. I think many of the companies found that H1B visas or bringing in help from other countries is not really cost effective in the long run, because you have to bring those people up to speed. You spend about a year of time to train them and bring them up to speed. And then they work for a few years, and they get enough money to retire, okay, in a different country. So what they do is they take all that knowledge with them and leave the country. You don't have to worry about those workers, trying to stay behind as illegal, immigrants, because they don't want to. Okay, they make so much money by comparison, over a few years. They're ready to retire. They go back home and they retire. Okay, they have no interest in staying in the United States. So now they bring a new batch of people, and they have to retrain, and all that knowledge will be gone in a few years again. So it's just not effective, not cost effective in the long run. So I think the trend is to try to train more people, kind of local, like within California, to basically fill in all those job openings. Because right now with Facebook and Google, has anyone checked how much you get paid as a seasoned software engineer working for those companies? Nobody has checked.
The base salary is like $128,000 at Google.
Yeah, that's base.
For a season, though.
Yeah, that's just base, and it goes up, from that point. Facebook, it's about the same, because Google and Facebook, they a lot of times compete for exactly the same people. Even for internship, they get paid, like $8,000. Yeah.
Yeah, I was really surprised. Those internships, you get nothing.
Yeah, I can afford to commute from Sacramento if I get paid that much money, right? I mean, that's like a non-issue. I can live on the train. Reserve a car for me. I'll just sleep in the train. That would be fine. Yeah. So they want to bring that salary down, and the only way to do it is to have enough people in the pool, so they don't have to compete with each other to find the right people working for them. Okay, so what do you guys think? I mean, obviously this is going to impact you because you are moving into that exact industry,
So
right?
we should push against teaching it in high school.
Yeah, we should just keep doing
I think but personally, I don't think there's much to worry about. Okay, they can try to train more people, but I think the people with the natural knack to actually get it done right is not going to change. Okay, it's still going to be the same percentage of people who will excel doing this, even though they bring the training to more people. Okay, because I'll just pose a question like this. There are a lot of people, 6'5", 6'6", with the right physical build to become a good basketball player. But how many Michael Jordans are there? Or people who can play at the level of Michael Jordan? Not really a whole lot, right? If you watch, basketball games, there are players of the same physical build, but they cannot play the game, the same way as Michael Jordan. So I think it's the same thing with computer science, computer engineering, and stuff like that. A lot of people can get the training and do the work up to a certain point, but when you want people who can get it done at the next level, that percentage never changes. It just there's only so much people, or percentage wise, of people who can do it at a certain level. So we'll see. I mean, time can tell. In 10 years of time, we'll start to see, whether, it actually makes a difference or not. Right. So are there any questions regarding the processor that I have been working on, other than, please, Tech, give it a rest. I don't want to look at it again. Well, okay, I spent a little bit of time last night to kind of expand it a little bit. So I will kind of show you what I did. And then we'll move on to the instruction set and addressing nodes. There we go. So there is one new file for this class that I just uploaded last night. And some of you, well, I can actually check the statistics. I'm not going to do it now, but I can check the statistics and see how many people actually downloaded it already at this point. So this is the new one, Tech Processor 3, is something that I worked on last night. And this one is kind of a significant change compared to the previous one, because I started to put into the microcode engine. I'm not done yet, okay? I'm just starting out with the microcode engine, but it will at least show you what it looks like and how it is going to basically tie everything together, okay? I'm not done with it, it's still work in progress. But it will show you, let's see, this is a logic sim, and then the file is tax processor 3. Go. All right, so let's go ahead and take a look at the overall view first, and then we'll focus on one particular part that I worked on kind of extensively last night. So if you look at this picture, it has not really changed all that much from last Monday. Okay, on last Monday, we got most of these components in already, but this part is new. Okay, so we'll go ahead and focus on this part, and then we'll see how it connects to the rest of this design. So let's go ahead and zoom in a little bit and just slide over to the microcode engine. Okay, this is the microcode engine. So the microcode engine has a few components. The first component that it has is MCC. There are different names for this, but I call it MCC because it's microcode counter. Just like a program counter, it is nothing more than a simple counter. It counts up by 1 by default. Just click, 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 click. Counts up by 1 for each click. The output of the MCC, or the microcode counter, the output, which is the Q port of the register, connects to the address bus of another memory chip. But this time, this particular memory chip is not RAM, it is ROM. In other words, this is our read-only memory. Okay, it's our read-only memory, and this selection, for whatever reason, the connection is lost here. So I'm going to reconnect this part. The selection is always on. Okay, in other words, this particular ROM chip is always selected. Okay, it's always addressed because there's only one of it. Just like the program counter, MCC itself has a counter associated with it. This is an adder. And as an adder, I'm making the microcode counter add to 0 all the time. But the carry flag coming in is a 1. So effectively, I'm just adding 1 to the current content of the microcode counter whenever I clock it. The output, which is 1 more than the current value of the microcode counter. So if you look at the output, it goes into a mux, okay, like this. And then this mux can select that as the input. back into the microcode counter. So every time I clock this little pin here, it will update itself to become one more than what it was before. Okay, and that's the same principle as the program counter itself. It has a path to go back to itself, and then every time I clock it, it increments by 1. That's why it's called a counter, because that's just basically what it does. Okay, the other part of the mux, the other input of the mux, comes from somewhere else, and I'll show you, where it comes from, when we get to that part. What is also kind of interesting is also this ROM chip here. When you look at this ROM chip, it has memory content, stuff like this. Okay, this is not exactly what I had last night because I was already working on the microcode. But the output of the ROM chip, if you look at the D port of the ROM chip, is not. I'm not looking at the 8-bit wide data bus as one single bus anymore. I split it up into 8 individual bits, and each bit. Okay, not all of them. I still have 2 more bits that I have not assigned yet, and I think I have to increase the width of the output bus because I'm running out of bits already. But when you look at the output bits here, let's just track down one of them. Let's track down bit 0. Okay, bit 0 goes all the way down here, goes all the way here, and then it goes back to the mux itself. In other words, bit 0 of the output of this ROM is going to actually hook up back into the mux to say, okay, am I updating the register MCC from just the incrementing mechanism, or am I bringing in the new content or the new value from somewhere else? Okay, there are occasionally occasions where you want to bring it in from somewhere else. And this is this is bit 1. Bit 1, if you track it down. This is one feature that I wish this particular program has, is to label a line so that I don't have to track it down like this. The other one goes to the other mux. This mux is selecting the address bus, which register becomes the address bus of the RAM chip. Okay, so we can either go from the indirect register or the program counter itself. So you can see the program counter is here. It feeds into one side of the mux here, and then this one feeds to the other side of the mux. In other words, bit 1 of a microcode memory location specifies, okay, when we are going to address RAM, who is going to specify the address? The indirect register or the program counter? The program counter is in charge of keeping track of which page of instructions we are executing when you run a program. The indirect register, on the other hand, is really just there. Okay, I can see that you want to do an indirect address, or you want to do a dereference. So which location do we want to access? That's the job of the indirect register. So they both have to access the data bus, the address bus, and this mux here is the one that is in charge of directing the traffic and say, okay, whose turn is it to specify the address on the address bus so that I know which location is going to be accessed. Let's take a look at bit 2. So bit 2 is this one here, and if you follow bit 2, it goes all the way around here, and it goes into the select bit of the RAM chip. In other words, it says, okay, am I ready to access RAM? Okay, is the next operation going to be RAM based, and I need the RAM chip to pay attention at this point. Bit 3, which is this one here, it goes to another pin of the RAM chip. It goes into the load pin of the RAM chip, which is the one that controls whether the next operation is a read or a write operation. If this one is if it is a 1, it is a read operation. If it's a 0, it means we have a write operation pending in the next clock cycle. Okay. Let's take a look at bit 4. Bit 4 is this one here, and this one goes, bit 3. Okay, we look at bit 3 first. So bit 3, is that bit 3 or bit 4? That's bit 4. So the bit 4 goes all the way across, and it connects to this little component here, which is our ALU, and it also connects to this mux here. In other words, it's basically saying, okay, are we going to pay attention to the output of the ALU? Okay, is this after a calculation, an addition or subtraction, and we should pay attention to the ALU. So eventually, this is not entirely done yet, okay? But eventually, if I zoom out, eventually what I want to do is to bring this pin here, which is our register write enable, this pin here, register enable 0, register enable 1, the pins into the indirect register. We want to bring all of those pins onto the data pins of that ROM chip that we are talking about. Okay, so by clocking through the ROM chip, we can now put out a sequence of ones and zeros into the control pins of all of the components in this particular processor. So this way we can say, oh, in order to read from a location in memory and put it into register A, this sequence has to happen. Okay, is that okay so far? As far as the concept is concerned. Okay, you probably already noticed some of these pins have already disappeared. Okay, they used to have a pin connected to a particular port of a component, and some of these are now connected to the data pins of this ROM chip already. So eventually, most of these pins will disappear, and all of those lines will eventually connect to one of these pins on the data bus of the ROM chip. So that the microcode engine will be in charge of orchestrating all of these components. The microcode engine is a conductor, basically. If you look at it, if you look at this whole picture as an orchestra or a band, okay, we have flutes, we have the trombones, we have trumpets, we have the percussions, we have the violins, we have all the musical instruments, okay, and they each has its own thing to do, in order for the entire thing to work correctly. The conductor is the microcode engine. The microcode engine is in charge of saying, okay, now you go ahead and get ready to start, and you go ahead and finish up, and you go ahead and da-da-da-da. And it's orchestrating the entire thing. So that's why all the control pins of each individual component eventually will bring back to the ROM chip or the output of the ROM chip of the microcode engine. And that's why I think the 8-bit width output is not going to be sufficient, because there are so many pins that are still dangling with this design that it's easily going to be a 16-bit width ROM chip. Are there any questions about the general idea of this processor design? Any questions? Okay. The only one pin, or the very few pins that will not be absorbed and put into the microcode engine, one is the reset pin. Okay, so let's go ahead and zoom into the reset pin here. The reset pin is external because the reset pin is asserted externally by some other circuitry to basically hold the processor in a reset state and wait for power to become stable. So as long as power is not stable, like it is still ramping up, or in a browned out situation, the reset pin is going to be asserted, so the processor will be held in a reset state, everything is going to be zeroed, and it's not going to do a single thing. The other pin that is not going to be rolled into the microcode engine is the clock line of everything, okay? So the clock line, the CLK line of everything, including all the registers, is going to be tied into what we call the system clock. So all of the components will basically share the same metronome, if you will, okay? So it gives that constant click, 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 click. So the whole thing, basically has to follow the same beat, as far as, the rhythm is concerned, okay? So that's, that's going to be all tied into one single pin. All the clock lines will tie into the same pin. So this clock here, this clock here, this clock here. Let's see, where else do we have clocks? This clock here, they will all tie into one single, basically system-wide clock pin. And that's basically what you're measuring, or what Intel is measuring when it says, we have a 2.4 gigahertz clock. That is the system clock. Okay, so each individual component listens to that one single clock because that is the one thing that synchronizes all of the operations. Any questions at this point? Okay. If there are no questions about this, I'm gonna give it a rest for the time being. Okay, But I will continue to work on this, so that when we talk about certain types of instructions, I'll give you an example of what actually happens inside the processor when we execute that kind of instruction. So this part is kind of new this semester. This is just something that I started this semester. But I think it will help your understanding of the assembly language instructions, because now we get a kind of more of an inside view of what is happening in the processor, as opposed to, oh, okay, this is kind of like still like C programming, because it's just source code to me. All right, so I'm gonna minimize this, in case we have to refer to it again. And at this point, we're gonna continue our discussion of addressing modes and one single basic operation, which is the move instruction. We talked about these three operands. Okay, so we'll go ahead and kind of start with this part again. An operand is basically just, you consider an operand a parameter to a function, to a subroutine. Okay, so when you call a subroutine, you have to give the subroutine certain arguments and say, well, let's just take I think last time we used a string compare or string copy, right? So when you call string copy, what do you need to give string copy to get this job done?
Memory location of where you want to write to and where you want to.
Exactly, a source and a destination, because the job of string copy is to copy a string from one place to another place. So in order to get it done, you have to specify where is it copying from and where is it copying to. That makes sense, right? So with a lot of operations at the level of assembly language programming, they also require additional information, like the move instruction, which is basically copy. So where am I copying from and where am I copying to? The operands, which are basically your arguments, there are three main categories of these things. The first one is immediate, which is basically as a part of the instruction itself, it tells you the value that is being copied from, usually, okay, well, always. So it is actually a part of the instruction itself that contains the value or the operand itself. Okay. Is that okay so far? It's a constant. Okay, it cannot change, because you are not supposed to change instructions while your program is running. So that's the first type of operand. I'll give you examples later on. The next one are registers, and registers as an operand basically means we are either using a register as a source or using a register as a destination. Okay, so the content or the value or the bit pattern of a register becomes either the source or the destination of an operation. Any questions about the registers in general? And last time, I used a spreadsheet to show you all the registers of the i386 processor, or the main ones, the 8-bit registers, the 16-bit registers, and the 32-bit registers. So we'll come across those things again today. We'll talk about it again. And then the next one, which is the only one left, is memory. In other words, instead of being a part of the instruction itself, instead of coming from a register or going into a register, a memory operand is the content of a memory location. Okay? And that's it. Okay? It's just a memory location. How we specify that location? Well, that depends on the addressing mode. Okay? So when it is a memory operand, then we also have to think about what we call the addressing mode. In other words, how do we specify the address of the memory location that will either supply the bit pattern or will be storing a bit pattern. But nonetheless, it is in the memory. So are there any questions about these three different types of operands and how to differentiate between these three particular operands? Yep, go ahead.
Memory is just the address?
No, memory operand is the content at a certain location in memory. And you do have to specify the address somehow, but it is not the address that is being copied, it is the content at a certain location that is being copied, either from or to. That's a good question. Any other questions regarding these three operands? No questions? All right. So if there are no questions about this, we'll start to go into addressing modes. I'm going to change the order of the introduction to the addressing modes. Okay, I kind of have to talk about the memory section, memory allocation, and this stuff too. But we'll, in time we'll get all of that stuff. So instead of reading the addressing modes sequentially like this, I'm going to start with immediate, and then we'll go to register. I will skip direct and go to indirect addressing mode right after. So it's going to be 5.1, 5.2, and then we'll jump to 5.5, and then we might go back to the other addressing modes. Okay, there's a reason why I'm going to skip around a little bit in this case. All right. So are there any questions before we move on? Okay. If there are no questions, and we'll go ahead and start with a program to demonstrate some of these concepts. So we'll go ahead and write a program. So it's going to go from immediate to register. That's basically what this program is going to do. It's going to use a move instruction to copy an immediate operand, which is a part of the instruction itself, to a register. Okay. I think we did something like this last week as well. But since it has been a week, it doesn't hurt to kind of talk about this again. With almost every single program, it really helps to say .text first. Now this is also something that is in the other slides or in the other topics. .text is telling the assembler what follows is going to go into the code section of this program. Okay? When you run a program, there are two parts in memory that you have to deal with, at least two parts. One part is the operation manual itself, and the other part is kind of like a scratch pad. Are we doing okay so far? So one kind of translates to the C code, like all the control structure, all the subroutines and stuff like that, and the other part corresponds to the global variables, the local variables and whatnot. Okay. So in this case, .text specifies that we are talking about the operation manual, the instructions, not the data that you have to use when you run the program. The next one is .global_start, and there's a space between the underscore and global. .global_start is a directive to the assembler. It's telling the assembler and say, you know what, somebody else may be interested in the location of this label called _start. So make it available to the linker, okay? Make it visible to the linker. Because without .global, all labels that you define inside the source file, it is only visible within the source file, but none of the other source files can see it. So this is what we call, you can consider this export, okay? We are exporting the label _start so that the linker has visibility of this particular label. Now _start is a very special label as well because it is the entry point of your entire program. Consider this almost like main in C and C++. This is the entry point of your entire program. So that's why it is really particularly useful. And after this, you can start to write your program. Okay. Now I'm going to do something that is kind of really useless. In other words, I'm going to start with two no-op instructions. NOP stands for no op or no operation. They are actual real instructions, except they don't do anything. It's kind of like a filler type of instruction. It takes up memory space, it takes up memory cycle, but they don't do a single thing. That's why it's called a no-op instruction. Okay. So what I'm going to do is to put two no-op instructions here, and then I'll define the label _start. To define a label, it's kind of like defining a label in C and C++. How many people have been introduced to the concept of a label and go to in C and C++? Kind of like this type of syntax to define a label. Okay, one person, that's okay. But in assembly language programming, we have to use labels and go-tos because there are no other ways to implement control structures in assembly language. So getting back to the label, this is basically just a bookmark and say right after the second no-op instruction, this memory location is also known symbolically as _start. That's basically what a label is. It's just a way to mark a place in memory and say, instead of calling this like right after the second no-op instruction, we'll give it a name. underscore start is the name of that label. Are we doing okay so far with that concept? Okay. And now we can actually do something about our instructions. So I'm going to use a move L instruction, which is move long. Move long means we are moving 32 bits. Okay, L as a part of an instruction means 32-bit. So we are going to move $ means this is a prefix of an immediate operand. So whatever follows the $ can be a huge, long, complex expression, but whatever the value of the expression is becomes the immediate operand. It becomes a part of the instruction itself, and it specifies the source. In this case, it is this is what we're copying from. So we can just give it a number, okay? And you can specify the number in decimal, you can specify the number in octal or hexadecimal. For the most part, the assembler understands the same number notation as in C and C++. In other words, if you want to specify a hexadecimal number, the 0x prefix works just fine in the assembler. If you want to specify an octal number, you use a prefix of 0, and anything else is decimal. So if you want to use a decimal number, you can just say 45. That's a decimal number 45. So most of the things that you understand about number representation and bases and stuff like that in C and C++ still works in the assembler. Okay, so that's really kind of helpful. So let's say we want to move a constant of 4512 to a particular register. So when you specify a register, you have to start with a % symbol. The % symbol, you can look at it as a prefix of a register. And there are quite a few registers. EAX is one of the 32-bit registers. So we'll just go ahead and copy this constant 4512 into the register EAX. And that's all I want to do. Okay? And to get out of a program, I'm not going to explain why you have to do this, because eventually we'll get to that topic. 0 into EBX and int $0x0. So these three lines, I'm not going to explain what they do, but I can just tell you that they are equivalent to exit 0 in C and C++. Okay, it gets you out of this program. All right, so this is a fairly simple program, but it's going to illustrate quite a few concepts already. So we'll go ahead and get this program ready to run. And the first one is to use the assembler. Gstabs, I think it's Gstabs, means we want to include the symbol table so that we can use the debugger later on. -O specifies the output of the assembler. So this is going to be immediate register.o, which is the object file. And then you specify the source code as the last parameter, or the last argument to the assembler. So at this point, at this point, we have two files related to this particular program. The first one, which is the .o file, is the file that we just created in the assembling process. The second file is the source file. The file that ends with .s is the source file. And after we have the object file, we have to do the linking. And the linker is LD. And with the linker, you have to specify the output file. So I'm going to name the executable immediate register. And the input is the object file. So you have to give it a .o file as the input. So after we run that, we will see that we now have three files. The first one is the executable. Now, with an executable, you can just run it. Okay, it doesn't do a single thing because this program does not have input or output, so it doesn't do anything at all as far as the outside world is concerned. And we will be writing programs like these for a certain amount of time, where the program is not interactive. There's nothing that it outputs. There's nothing that it inputs. So how do we deal with programs like this? GDB, exactly. So we say GDB and then the file name, the name of the executable, and that will load the program into memory. And also, because I assembled the program using the -gstabs switch, we are also including the debug information. So with the debug information, you can now start to see, oh, okay, but this is exactly the same program that we, compiled earlier. So now the question is, if I stop the program on line 3, is it ever going to go there? Okay, so we'll put a breakpoint on line 3. There's nothing wrong with putting a breakpoint on line 3. And I'm going to put a second breakpoint on line 6. So what this means is if the program ever gets to line 3, it's going to stop. If it ever goes to line 6, it will stop on line 6 as well. So when I run the program, I want to know, is it going to stop on line 3? Because those are instructions before line 6. Or is it going to stop on line 6? Because that's the entry point of the entire program. What do you guys think? Yep. Line 3 is not reachable. It's not reachable because it is before the entry point label. Okay? So let's go ahead and run the program. R runs the program, and it stops right away on line 6 and not line 3. It will never get to line 3 in this case. Okay? So when we get to line 6, it kind of helps to look at the value of EAX. So you can use print $EAX to show the content, the current content of the register EAX in the debugger. Okay, so the $ takes on a different meaning when you're inside the debugger. I know it's kind of like, there's a lot of stuff to know, to remember, but when you do it a few times, you'll start to remember. Okay, this is the kind of things where it's kind of like muscle memory. You just have to do it a few times and then it will be okay. Then we'll single step on line 6 and try to print EAX again. And you can see that EAX is now 4512, which is exactly what you would expect because we are copying the value 4512 to register EAX. So that's exactly what it did. No problem. It's good. Are there any questions about this particular program? Go ahead.
So it just skips over the no ops just immediately?
It's not quote unquote skipped, it's just that we never got there. Because when we ran the program, the debugger, basically the loader, whoever puts the program into memory and start execution, will use _start as the entry point of the entire program. So we start execution at the label _start. Now, if you have some control structure, you can go back and forth and be able to execute code before _start. But this program does not have any way to go back to the instructions before the label _start. And that's why label on line 3 and line 4, those no-op instructions are basically unreachable. So it's not really kind of like we skip over, we just start at a place after them. Yep.
And if you don't put a label, does it start right afterwards?
Aha, that's a good question. What if you don't have an underscore start label? If you do not have a label called _start, the linker is going to complain and say, hey, nobody is telling me where to start the program. But it's only a warning message because the linker would then become, become a smarty pant and say, well, if nobody's going to tell me, I'm going to make a guess, okay? I'm going to assume the very first instruction is the entry point. Right, so then it will start with line 3.
Okay.
Yeah. But you don't want to leave it up to the linker to make that default decision. You always want to specify this is the entry point of the program. And that is even more important when you have other files that you have to link with, because then the ordering of the linking is important. So you're not guaranteed of the same entry point every single time.
So could you have multiple entry points on the same file?
No, you can only have one single entry point to the entire program, because when the operating system loads the program into memory and start execution, it needs to know exactly where is the entry point. It's just like you can only have one main function in C and C++. That's the entry point of your entire program. Yep.
Does the entry point label have to be prefixed by underscore?
Yes, it has to be prefixed by an underscore. So the label _start is special.
Does it have to be underscore start, or is it just start?
It has to be _start.
Could it just be a blank underscore? Just underscore and then nothing afterwards? Or there has to be something afterwards?
It has to be _start all in lowercase.
Oh, okay.
Yeah, so that has to be exact. Okay. Any other questions about this? Okay. If there are no questions about this, then we'll move on to the next one. Okay. So the next one is going to be, Okay, so we have just talked about the immediate operand. You know, basically anything preceded by a dollar sign is an immediate operand. The next one we also used already is the register. This is where, you know, last time I gave you a spreadsheet with, you know, color coding, you know, with all the 8-bit registers, 16-bit and 32-bit registers. So I'm not going to repeat, you know, all that discussion because it's already recorded, it's online already. But the important part to remember is you have to use a prefix of a % symbol before you refer to a register. Okay, that is mandatory. Okay, so we talked about this already, and we're going to move on to the next one. The next one is the one that I want to skip over, so do not, you know, at this point I'm not concerned about this one. And here's a digression. Okay, the digression I do want to go over a little bit. Probably not. Okay, no, I'm going to skip over this one as well, at least for the time being, and then we'll come back and talk about it. So right now we have the indirect addressing mode. The indirect addressing mode looks kind of like a register operand, but it has one difference. If you just look at the instruction here, how is this different from the one before? Parentheses, okay? When you put parentheses around a register name, it becomes an indirect addressing mode or indirect operand. Now the indirect operand is not, so in this case, EAX does not specify the destination itself. EAX is used as the address to specify which memory location is the actual destination. Am I doing okay so far?
Say that.
Okay. In this case, the destination is not the register EAX. Instead, EAX is specifying the address of the memory location that will be changed by this instruction. And that's why it's called indirect. Look at this as dereference. Okay, in C and C++, it's the same thing as an asterisk after before a pointer. We are not changing the pointer itself, we're changing what the pointer is pointing to. And the pointer, in this case, is EAX.
Register.
The register EAX, yes. Are we doing okay so far with this concept? Kind of? Okay, let me switch back to the processor design. You know, this is why I do the processor design, because I think, you know, this may be helpful in terms of, you know, showing you what is happening here. When you have a register operand, it is the registers that is changed. Okay, so when I specify %EAX without the parentheses as the destination, one of the registers within the register bank, which is what I have selected here in this picture, is going to be changed. And that's the only thing that's going to be changed when you specify a register operand as the destination. But what I have right now is the content of one of these registers is going to go into the indirect register. And then the indirect register in return will drive the address bus of the memory chip here, and one of the locations in memory is going to be modified. And what the register is doing is to serve as an address to basically specify, okay, you know, which location do we want to modify? Well, let's check this register here. This register has a value of, let's say, 63. So location 63 in memory is what is going to be modified. Is that okay so far? Okay. Well, let's go ahead and see if we can do a little demonstration of this particular addressing mode. So we'll go ahead and say immediate to indirect. Okay. So I'm naming the file, you know, using the addressing mode that is used in the file. So same as before, .text. Now .text is not strictly required because by default it is already in the code section. But in this case, in this particular program, eventually we'll get to the data segment. So this is going to be useful eventually. So we'll go ahead and write a program that is not going to run correctly. So we'll go ahead and first move something into the register EAX. So we'll go ahead and just randomly pick a location or pick a value was it 6512? Okay, so we'll copy the same value into EAX, and then in the next instruction, I'm going to have a move byte, a constant byte of 0 to the 1 byte location, indicated by the content of EAX. And then we'll have the usual stuff. This stuff is not really needed because I never really traced this part of the program. But as a good habit, I always want to have it available. So here's the program. Okay, same program as last time, except there's a new instruction, which is this one here. Okay. So when you read this program, you just read it and go like, okay, the first instruction is going to copy the immediate operand or the exact value of 4512 to a destination of EAX. Okay, so EAX as a register is changed by the first instruction. We observed that last time already. Is that okay? So the next instruction, the second instruction, is saying, okay, here we have another copy instruction or move instruction. This time we are copying a byte, the suffix of B indicates this is an 8-bit operation. So we are copying a bit of zeros, okay? Just basically 0, 0, 0, 0, 0, 0, 0, 0, to not EAX, but where EAX points to. So we are going to attempt to change the byte at location 4512 in memory. That is what the second instruction will attempt to do. Is that okay so far? Okay. So let's go ahead and see how this program runs. So once again, we assemble with G stabs as the as a switch, so that we have the debug information in the object file. And this is immediate indirect .s is that's the name of the output, and that's the name of the input. And then we have the linker, specify the output to be immediate indirect, and then the input to be immediate indirect .code. Oops, I forgot. I forgot to specify the underscore start label, and this is exactly what you will get. Okay, if you forget to specify the entry point of the entire program, it makes the assumption and say, since you didn't tell me where to start, I'm going to assume this is the place to start the program. Now, for this particular program, it's going to run just fine. I don't have anything extra before the starting point of my code, so it's going to work exactly the same way. But it's not a good idea to leave any warning messages unfixed. So I'm just going to go back and change it. There we go. That will fix the problem. So I have to reassemble and then relink in order for the change to become effective, because the object file is created from the source file, and then the executable is created from the object file. So when you make any changes to the source file, you will have to reassemble and relink. Okay? Okay, so now the linker is not complaining. We can now start to run the program. If I just run the program without using a debugger, segmentation fault, which is the same thing as in Windows. How do they call it? Something exception.
Unhandled exception.
Sorry?
Unhandled?
Unhandled exception?
I'm not sure.
Yeah, but I think different versions of Windows refer to it slightly differently, but it's the same thing. Okay, unexpected exception or something like that. In Linux land, it's called segmentation fault. Generally speaking, a segmentation fault is basically the operating system complaining and say, hey, your program is trying to access a location that it's not supposed to. That's what it means. Okay. Okay. So what does it mean when we have a program doing this, and how do we debug a program when this is the result of running a program? GDB is the answer. Okay. So if I just run the program without setting a breakpoint, it will tell me that it received. Okay. The concept of a signal, we're not too concerned at this point about what is a signal, but the program stops on line 5 of this program when it's attempting to move B $0 to indirect EAX. That's the problem. Okay. So what this is telling me is location 4512 is not a location that my program has access to. Okay. I'm not convinced. I'm going to try it in GDB itself to get to that location and make sure that that really is the cause of this problem. Okay? So there are two things that I need to do at this point. First thing first, I need to confirm that EAX does have the content of 4512. No, I mean, just in case it got corrupted and it has some other values. Okay, so now I have confirmation that EAX does have the value that we think it should have. And then what I'll do is I'm going to say, let's go to location 4512 and see what is there already at this point. Okay? Does anyone know how to formulate a C expression just to read location 4512 as a byte? Come on, you guys have all taken C and C++ already. This is pointer stuff. Okay, so let's go ahead and see how we can construct this. Okay, so we want to go to location 4512 and read back the content at that location. So that implies what? Dereferencing, right? So to do dereferencing means we need an asterisk like that. But asterisk 4512 is not going to work because when you do dereferencing, you have to say we are dereferencing this location 4512 as a what? As an integer, as a char, as a structure, as what, right? You got to specify. So the first thing you have to do is to say, oh, 4512 is normally just an integer, but this time I want it to be a location. So you have to cast it into a pointer first. So since we are trying to access an 8-bit location, we have to cast it to a char pointer first. So you say char asterisk, and that will turn 4512, instead of looking at it as an integer, now it is seen as a pointer, as a location of a byte. Now you take this entire thing, which is now a char pointer, and you say, let's go ahead and dereference that. So you put the dereference operator outside of the entire thing. This will attempt to read location 4512 as a byte. Are we doing okay so far? Is this kind of reminding you about all the pointer stuff that you learned in C and C++? Yeah. This is actually important stuff. Pointers are the reason why we have to learn C and C++. Okay, so let's go ahead and try that. Okay, so we'll dereference the char pointer of 4512, and it tells me cannot access memory at address 1180. Hey, what is that? 1180. It starts with a 0x prefix, which means it is a hexadecimal number. It's base 16. And it kind of makes sense to me because in base 16, 1000 is 4096 in decimal. So the value comes out to be about right, in the right range. Okay? So I really cannot read from that location. What about writing to that location? How do I make the debugger write to a certain location? You can use the command called set. And if you cannot remember how to use it, you can always say, help set, and it will basically remind you how to, use the set command. You can set a particular variable to something. I think it's just set itself. So we can say set char pointer 4512, and then you can specify the equal symbol, and we'll put a 0 here, and then it complains the same thing. Cannot access memory at location 1180 in hexadecimal. Okay, so that location really is not accessible by me or by this process, this program in execution. Okay, but why? Now that we know that location is not accessible to this particular program or this process, oh, by the way, what is the difference between a program and a process?
Program is a series of processes?
Kind of the opposite. A process is a program in execution, an instance of a program in execution. In other words, every time you use a debugger to look at something, you're looking at a process. Okay? But a process always has to correspond to a program, because you're running a program. A process is a program in execution. But you can potentially have multiple processes corresponding to the same program. You can run the program multiple times at the same time in parallel. So you can have one single program, but multiple processes corresponding to that one single program. Okay? So this process has no access to that location 4512 But why is Linux so restrictive? Why can I only access certain locations? Why not just leave the entire memory space to me? Name one. Okay, go ahead.
Is it because that's where the kernel is?
Well,
The memory that the operating system needs to use, you should be able to access.
it's kind of like that, but it's also more like this particular program, this process, only needs to access a very small portion of memory because it really doesn't use memory at all. So the kernel is only allocating like this much memory corresponding to this program. When you try to access outside of this range, there's nothing allocated to those particular locations. Those locations do not map to actual RAM locations because this is virtual. This is not real. This location is not actually the location on the memory chip. This is only seen from the program's perspective. Now that brings up a very interesting question. If I try to run this program like 6 times, go through 6 different sessions of GDB, each session of GDB will say the program starts at the same place. How can that be? It's because they're all virtual. Okay? Each program has its own memory space that is completely separated from other programs' memory space. Or process, I should use the word process. Okay? And that is because Linux is a protected operating system, or an operating system that is using the protected mode of the processor. Name one operating system that does not have memory protection. ZOS. Windows 95 or earlier. 98, Windows Millennium is the last one that does not have memory protection. The relevance of this question is kind of going away because most of you do not even remember Windows 95. Okay, in Windows 95 or DOS, back in the DOS days, or Windows 3.1. Okay, Windows 3.1 was the first operating system that has the ability to run multiple programs at the same time. In the DOS days, you can only run one thing at a time, so memory corruption across application programs is a non-issue. Okay, you can run WordStar. Then you have to get out of WordStar to run Lotus 123. Okay, so there's no chance one application can step onto somebody else's territory and cause problems. Windows 3.1 was the first environment where you can run programs at the same time concurrently and have both programs up and running at the same time. So without memory protection, it's kind of like everybody has access to the entire memory space. If Microsoft Word decides to, I just feel like accessing that particular location, okay, and that turns out to belong to another process, let's say Microsoft Excel. So by the time execution goes back to Excel, the Excel process is going to run kind of strangely because it has been corrupted. Its memory space has been corrupted. Okay, and back in those days, Windows 3.1 all the way to Windows at least 98, even the operating system is not protected. So your application can actually alter memory locations that belong to the operating system itself. So that's why one misbehaving application can host the entire operating system. It just locks the whole thing down and it just stops the entire thing. Okay, but these days when we have Linux or Windows NT, all versions of Windows after XP are NT based, so it is already protected. So if one application is misbehaving, doing something like that, that particular process will die. Okay, but nobody else is going to suffer anything because the operating system is saying, here's your memory space. If you do not play nice with your own memory space, I will stop you. Okay, and you will stop execution. But nobody else is going to be affected because they do not share, they do not overlap memory spaces. Is that kind of okay with you guys, the concept? Okay. All right. So if this program is not running, how am I going to demonstrate this concept of indirection? Because I want to demonstrate the concept of indirection. So this is when we need to go to the data section and basically say, give me another binder, okay? Because .text is basically saying this is the instruction binder, the operation manual. So now I want a second binder as a scratch pad. It's like, okay, this stuff I need to keep overwriting all the time, so give me something that I can overwrite. And when you do something like that, you can now start to allocate and say, I need 4 bytes to store something, okay? So if you want to use 4 bytes to store something, you can use .int, okay, which is a directive to the assembler, and give it an initial value. Whatever initial value you want to use, it's fine. So in this case, let's say the initial value is in hexadecimal ABCD 1, 2, 3, 4. Okay. So what this is going to do, the .int 0x ABCD 1, 2, 3, 4, you're telling the assembler and say, in the data section of this particular program, reserve 4 bytes. Okay. And not only reserve those 4 bytes, make sure those 4 bytes start with the content of ABCD 1, 2, 3, 4 as a 32-bit integer. Okay. Is that okay so far? Kinda? Yep.
Does it need to be indented, or are you just doing that?
Now I'm just doing the indentation because I'm going to put something else that is going to be not indented before that. Okay. So that's good. Okay. So now we have certain locations allocated for this particular process that is intended to be overwritten eventually. Okay, so that's good. Now the question is, how do I refer to it? How do I refer to the location that is corresponding to the .int directive? I don't have a way to refer to it. Well, I just have to use another label, right? So I'm going to use another label here. Now, since this particular label doesn't really serve a particular purpose, I'm just going to use L1 as the name of the label. It's kind of like a generic label name. So at this point, I have L1 as a bookmark, as a label, to basically say the first byte allocated to .int, blah, 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 is also known as label L1. So now I can use L1 to refer to that location. Is that okay? All right. So with this, now I can start to go back to my program and say, oh, don't try to access location 4512. Go ahead and access location L1 instead. L1 is just a number, okay? It is just an address in the memory space, and any address in the memory space is really just a number, okay? So if I can use 4512 after the $sign, there's no reason why I cannot use L1 as a value to copy into EAX. Is that okay? Okay. Are there any questions about what L1 really is and why we can put it after the $sign so it becomes an immediate operand? Yep. Go ahead.
But it's not the real address for that, right? It's like the virtual one the operating system gives the program.
This is virtual. This is as far as the process is concerned. It knows that location by the name of L1. Any other questions about this? Yep.
Do you not have to put an end to the label so it knows when it's
And to the label? No, you don't have to.
So, because with start, it's saying there's start, everything after that's in start.
Right.
And then you have L1, and everything after that's L1.
No,
Start,
no. L1 and underscore start. A label is only a label of a single byte in memory.
Okay.
Yeah. So when you talk about a label, as an address, it is the address of a single byte, because the assembler has no concept of type. So each time you refer to a location, it's a location of a single byte.
All right.
Okay. So this particular program is going to illustrate some interesting parts of assembly language programming that you will never have to understand in C and C++ programming. So we'll go ahead and reassemble, relink, and then GDB program first. List the program and put a breakpoint on line 7, okay, because that really is the first part of the program that does anything useful. Okay, so we'll go ahead and run the program. We are just ready to copy the value of label L1 into EAX. Now remember, this is not copying the location. This is not copying the memory location at L1 to EAX. It is just copying the label to L1 to EAX. Does everybody understand the difference? Okay. So let's go ahead and go through this one instruction, and then we want to see, okay, exactly what was copied into EAX. Whoa, some big number here. Now, if you want to print a number in hexadecimal, you can always specify /x to specify I want to print it as a hexadecimal number. So it corresponds to location 8049088 in hexadecimal. Okay. Great. How do we know that really is the location that has the 32-bit integer that we specified earlier? There are two ways to do this. Okay. One way is to use the print command. You can use the print command and say, let's dereference that location, but dereference it as a 32-bit integer. So in this case, because it is a 32-bit platform, int by itself, is implying it's 32-bit. So we'll go ahead and say print at the location of 0x8049088. And there's an easy way to do this. I'm going to show you the hard way first, and then I'll show you the easy way to do this. Oh my goodness, it's trying to print it in a decimal format, which is kind of difficult to verify. This is actually ABCD1234 in hexadecimal, right? So can we do something like a /x? Yeah, we can certainly do that. So we can do a print /x instead, and this time we use the same thing here. But I don't feel like copying that number anymore by hand, okay? And here's the really, really cool thing you can do. You can just refer to it as $1. If you put a number after the $sign in the debugger, it basically refers to the result of a particular command earlier. So in this case, $1 is the value of EAX from before. So just by using $1 here, it is going to refer to that result, which is great, right? I mean, this means you don't have to, copy those huge big long numbers. But you can also refer to that as $EAX because it is the value of the register EAX. So it serves exactly the same purpose. Are there any questions about these commands of GDB? Questions? Well, you will when we have homework assignments because these are really, really useful commands. And we got ABCD1234 back. So that means location 8049088 in hexadecimal does have the content of ABCD1234. That's great. Now we're going to single step the next instruction. In other words, we're going to run this instruction next. Single step. It's not going to cause a segmentation fault because it is memory that belongs to this particular process. In fact, it is not just memory for this process, it is data memory for this particular process, which means we certainly have the rights to overwrite those locations. But now I have a new question for you. We have a move byte instruction, which means it's only going to copy 8 bits, 1 byte, to overwrite that location. So the number used to be ABCD1234. What should it be now? 34? Okay. Does everybody understand the question, the nature of the question itself? Those 4 bytes at location 8049088, the 4 bytes combined, 32 bits, used to represent the value ABCD1234 in hexadecimal. I just overwrote one location with 0 as a byte. So the question now is, how is it going to impact the 32-bit integer? Because a 32-bit integer does not fit in 8 bits, right? That makes sense. So when we overwrite only 8 bits or 1 byte of a 32-bit integer, it's only going to impact one part of the 32-bit integer. Which part is going to be impacted? That is the question. The least significant part is the correct answer. Okay? And that only is because the Intel processor is what we call a little endian processor. Okay? Well, first of all, let's confirm that first, okay? And then I'll go back and explain what is little endian and what is big endian. So let's go ahead and repeat the previous command and look at that location again. And sure enough, the least significant byte is changed. Now, I know it is just the least significant byte because in hexadecimal, each hexadecimal digit is representing 4 bits. So 2 hexadecimal digits will represent a single byte. And in this case, the least significant byte represented by 2 digits are zeroed by the instruction, moving 0 into where EAX points to. Are there any questions about this particular code or the effect of the program?
Doesn't it get confusing looking at previous like breakpoint and stuff? You see that it's the immediate value of 1 or something like that, and you have $1 as your output for your debugger, and using that as value.
Yep, you will have to get used to it. The notation between the assembly programming language and the notation used by GDB can lead to a lot of confusion. It's not just the use of the $, it's also the use of what is considered a word, what is considered long, and so on. So they can lead to a bit of confusion. But this is the only reason why it is changing 3-4, the least significant byte, and not AB, which is the most significant byte. The only reason for that is because the Intel processor is what we call a little endian processor. On the little endian processor, the least significant byte of a multi-word integer is the one that has the lowest address. Okay? And in the big endian processor, it's the opposite. Okay? The most significant byte of a multi-byte integer is the one that has the lowest address. Can anyone name a big endian processor? PowerPC and also the 68000 family processor, and both were used by the Mac OS, the previous versions of Mac OS. Those are all big endian processors. Now, little endian and big endian also plays a part in TCP/IP, networking protocols. Now, why do you think it has anything to do with networking protocols? When you transmit an TCP/IP packet, it has to contain the IP address of the source and also the destination, right? And with an IP address, it's really just a 32-bit number. So now the question is, am I transmitting the most significant byte of the IP address first, or am I transmitting the least significant byte of an IP address first? So that's why little endian versus big endian, not only does it have impact when it comes to assembly language programming, it also has impact to anything that is serialized. Every time you store something into a file, you have to think about, is it little endian or big endian? Am I storing the least significant byte first, or am I storing the most significant byte first? Is that making any sense? Okay, and TCP/IP as a protocol turns out to be big endian. It transmits the most significant byte first and not the least significant byte first. Okay. All right.
How do you spell that? Andian?
Endian as an end, E-N-D, endian. E-N-D-I-A-N. Because I can see people with that song going in their head. Da 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 dee da da dee da. When you spell it with an I-N-D-I-A-N, then yeah. Okay. Some people are getting it.
I got it all.
Yeah, you're getting it. All right. So, this is kind of interesting, right? What if I change this program to something like this? What if I say, instead of L1, let's pick L1 plus 2. So this is perfectly okay. L1 is nothing more than a symbolic name of an integer. Can I add 2 to an integer and end up with an integer? Yeah, sure. I mean, if I start with an integer, adding 2 to that integer ends up with another integer. So what do you think would be the impact of this program? If I print the memory location as a 32-bit number starting at L1 after the move B instruction, what should I get when this program runs? Okay. In other words, if I put a breakpoint here, okay, the pound sign is the beginning of a line of comment, so you can basically put as many comments as you want in the program, starting with a pound sign on each line. So if I were to stop the program at this point and look at the location at L1 as a 32-bit integer, what should I be seeing? And remember, this is a little endian processor. The least significant byte is at the lowest address. So the question is, which byte am I changing in this case? The CD, right? So in this case, you know, the 32-bit integer should be 0xAB001234 in this case. Because 34 is the least significant byte, it is at the address of L1 directly. This is L1 plus 1, this is L1 plus 2. Okay? And this is something that you should do, you know, a lot, you know, when you're reading the notes and trying to understand the concept. Is not just to read it and think, okay, you know, I think this is what it means. Write a very simple program to test it, okay? To say, okay, if my understanding is correctly, this is what the program is supposed to do. And then go through GDB to verify that is really the case, which is what I'm going to do next. So now I go through the assembler, the linker, and then go into GDB again. And I'll put a breakpoint at exactly line 10. Okay. And the program is now, I'm running the program, and now we can go through the same thing, print /x to print in hexadecimal, dereferencing the pointer, which is an integer pointer, it's a 32-bit number, at the location of EAX. Okay, so EAX is used as an address to be dereferenced. And we get, oh, I know why. EAX is not the beginning of the entire integer because it is already offset by 2 bytes, so I should not be printing where EAX points to. This is the part that gets a little bit interesting because, okay, let's see if this will work. Yeah, that won't work. This is because of a, okay, this works because you have to put an ampersand before L1. It's a disconnect between GDB and the assembler. L1 is not understood as an address, it is understood as an integer, so you have to take the address of that. But basically, this is, you know, if we did change only this particular byte, and then all the other bytes remained unchanged. Is that okay so far? Sort of? Question?
Could you do that EAX minus 2 that you typed in? Like, does that work?
It may or may not work. I have to give it a try. Now, the trick to do this is this definitely is not going to work. Now, the reason why this is definitely not going to work or not do what we wanted to do is because typecasting is only typecast EAX in this case. So by the time we get to -2 or subtract 2, it is actually subtracting 2 from an integer pointer, which means it's going to off by 8 bytes. Okay, so we have to group EAX -2 in parentheses first, and then typecast the result of the subtraction. Because otherwise, we'll typecast EAX first, and then the -2 is going to apply to a integer pointer, which is what we want, which is not what we want to do. So this might work because EAX is just a number, and we can do that. Yep, so that worked just fine. I originally wanted to do this, but I didn't want to throw it out first, because I wanted to refer to just L1, which is the absolute location of that 32-bit integer. Right. Any other questions? Well, there's another way to visualize this. Okay, so I'm going to introduce another command in GDB that you will find useful throughout this semester. This command is simply X for examine. Okay, so when you do an examine, we can do something like this. We can examine a word which is 32-bit in GDB. Okay, so this is awfully confusing because W in an assembly language program is 16-bit, but when you're in GDB, it is 32-bit. Okay, so we specify the width, we specify the format, which is in hexadecimal, and now we can refer to exactly the same location, EAX -2. Okay, shows you AB 0, 0, 1, 2, 3, 4, just like before. Okay. Now we can do something a little bit different. This time I'm going to use a slightly different way to format it. The 4 is a count. Okay, the 4 means I want to print 4 of the following. What of the following? B is the same thing as in assembly language programming in this class. It stands for byte or a bit. So I want to print 4 bytes in hexadecimal starting at the location of EAX minus 2. So I'm going to start printing at exactly the same point, but this time instead of printing a 32-bit number, I'm going to print 4 byte numbers, okay, 4 bytes. So I'm looking at a 32-bit number as 4 individual bytes this time. Let's think about this and tell me what you think should be printed in this case.
0, 0, 1, 2, 1, 3, 4.
Well, remember it's little endian. When you print memory location, it prints it prints the byte of the lowest location first. Because we read from left to right, so the leftmost one is the one that has the lowest location. So knowing that, how is it going to print?
Backwards.
Okay, and
All segmented by byte.
okay, very good. It's segmented by byte, and it's going to print the least significant one first. But exactly what are the bytes that we are printing?
3, 4, 1, 2, 0, 0, AB.
That is correct. Not 4, 3, 2, 1, 0, 0, BA. In other words, the flipping, because of endianness, applies at the byte border. But within the byte, we don't do any flipping. Okay? So you have to keep that in mind. Now let's go ahead and double check. And sure enough, we are starting at exactly the same location, which is 8049088. It's a familiar location by now. And the individual bytes are printed now as 34, 1200, and AB. So the flipping of the significant bytes is only occurring between the bytes, but not within the bytes. Okay, you have to remember that. And the reason why that is the case is because the smallest chunk I can address with the i386 architecture is a whole byte. I cannot address an individual nibble, which is 4 bits within a byte. So endianness does not apply when we're dealing with a single byte. Is that making any sense? Okay, because if the memory locations are only byte wide, then we can only address all 8 bits at the same time, so endianness does not apply within a byte. Any other questions about the addressing modes that we have talked about so far? No questions? Okay. I know we are running out of time, but I do want to bring up one more thing, just one more. And it has to do with RISC versus CISC. Okay. And to do that, I'm going to bring up the notes first. I know you guys have to go, but this is kind of important. And this is the right time to talk about it, so that's why I want to at least get through this part. It's 5.6, So technically speaking, the immediate operand, the register operand, and the indirect operand are the only 3 operands that are ever needed with any type of architecture. Okay? So then the question is, how come we have all of these other operands, in the nodes? Okay, direct, base, addressing mode, and so on and so forth. There are like 10 more or 8 more of the addressing modes. So what are those for? Well, that's the main difference, or one of the main differences between a CISC architecture versus a RISC architecture. A RISC architecture means, in terms of hardware, it gives you the minimum. Okay, this is the core of what you need. Everything else you have to do it by instructions, do it in software. Yep.
Is it like ARM processor?
Yep. The ARM processor is is a commercial RISC processor, so it has a little bit, just a little dash of CISC to make it a more effective processor. But for the most part, it is a RISC architecture. The hardware gives you the minimal. Okay, it's like, okay, this is all that you will actually need. But for convenience, you will have to do it by instructions. Okay, you have to like group several instructions to do one kind of bigger thing. A cisp architecture, a complex instruction set computer, on the other hand, will basically give you the convenience of saying, oh, you know what, I know you tend to do a lot of these things a lot of times, so I will do it in hardware to simplify your software. That's the philosophy of a cisp architecture as opposed to a RISC architecture. So the way I'm going to teach this class is a little bit different from before. I'm going to look at the i386 as a RISC architecture. So I will give you only the minimum instruction set and the minimum stuff so that we can implement everything else in software instead of doing it in hardware. Okay? So it's a slight deviation from all the previous semesters because I think it is actually a better way to teach this class. Yep.
Is it a bit more, I mean, going with the RISC processor, is that way more ideal for like programming on smartphones?
No, it has to do with the cost effectiveness in terms of the hardware. And in the case of cell phones, it has to do with energy efficiency. Because a RISC architecture is always more, it consumes less energy to do the same amount of computation. Even though for certain things you have to use more than one instructions to do it, but overall speaking, you're not wasting silicon. And if you're not wasting silicon, you're saving power. All right, so we do have to move out because the next class has to come in. I'm sorry about being a little bit late today.